because Matlab not always ensure when the answer will be returned. So sometimes you have to validate your own results. If you change the parameters or algorithms in the parameter, the parameters in the algorithms, then if you are going to get the consistent answer, then you can trust the answer. Otherwise, you have to change the parameters again. So this is one example. Let's consider the DDE, delay differential equation, like this. And in this equation, you will see that on the left-hand side, there is the first order derivative on signal x at time t. And we have second order derivatives on y's or at time t. Apart from the signal, you may notice that there is a yt minus 1, which means the signal of y 1 second ago. There is a 1 second delay. If we use DSI, then we say that this is signal of y at 1 second ago, and this one is signal of x at 0.5, half a second ago. So they happen at different times. This kind of system is called delay differential equation. How can we solve this kind of differential equations? And in the lecture, I think I talked about the DE23 algorithm. We can easily solve the problem with use of that function. Now I'm going to talk about how can we solve this kind of delay differential equation with the use of Simulink. How can we do that? If we are trying to perform solutions on this kind of delay differential equation, what you need to do again is to define the signals. For instance, you can assign that this one is x at time t, and this one should be x dot at time t. And you can assign this one as y at time t, y dot, and y double dot. And also I think this one can be easily expressed by a transfer function. We do not have to use this low-level description. So what we need to do is to put a transfer function here. S squared plus 3s plus 2. And the numerator is 4 for this one. So this one is x, this one is y. Once you have done it, you can link these two signals together because they are all equal to x. So what about the first equation? This is a description to the second equation. So what is the first equation? In the first equation, we have to add a few signals together. One is a constant 1 for this part. And the other one is 3 times of x. So we have to use a gain here and connect it like this. This is the second one. So how can we model this part? This is a delay of y signal, so we have to use a delay term. And then link the signal here. And we have to set the delay constant to 1 in this case. And what about this signal? We also have to set a delay constant, a delay block here with a constant of 0.5. So this signal will be x t minus 0.5. So this signal we have two. The easiest thing you do is to use a multiplicator and a few that this one is X. So you can use this one to get the cubic function. Or, more simple, what you need to do is to use a mathematical function here. Again, we have to use SDN block. And then we can connect it like this. So what we should write here, 0.2 times U, we do not have to write 1 there, U cubed minus U. This is the last two terms. We assume that U equals to this signal. So we can easily fill the information to that block. Okay, so U is equal to X. U equals to X side at T minus 0.5. Because you have connected this one here, so U should be this signal. And this signal is happens to be X T minus 0.5. And here we can also write 1 here, but it is not necessary because U is a scalar signal. And also if we are happy, you can use brackets like this. It is the same. So this kind of notations are all acceptable. C7M CDE2, so this is the model I created. And you have to set the delay constant. For instance, for this one, this is a Y. Double click it, you will see that the delay constant for there is 1. And for this one, we have to put 0.5 as delay constant. In this way, we can easily model the delay differential equation. And we can click the icon. And since we use two output blocks, one is output, the other one is the scope. About it 1 over plus 3. Oh, it should be the same like this one, because you can consider that one as the transfer function also. This one you can consider it as a transfer function as well. Alternatively, you can describe it like this. It should be the same. And since there are two output devices, one is the scope, you can double click it to find the curve for that signal. Also, since you have used the output device there, the variable Y out will also be generated automatically. So in this case, we can also display the result by the use of plot command. You have to plot the relationship between T out and Y out. This should be the same as the one I obtained with the scope. So it seems to be quite easy to display the result. Or if you do not click the icon, then you can use a command line like this to find the simulation results. So it seems to be quite easy to do it like this. And if we are using, I think if we are using CDE23 command, it might be more difficult to describe it. So now let's consider